Hi everyone, I'm Simon Park and welcome to the Gillian Taster. Today, you will be seeing how the recursive list length function we've seen in the proof sketch is verified in a real-world separation logic based tool, in this case, Gillian. At this point, you should now be familiar with the list predicate and the proof sketch of the recursive list length function. So let's have a look at how all of these are implemented in Gillian. At the top, we have the list predicate, and at the bottom, we have the list length function implementation and specification. For the list predicate, you may notice there are a few syntactical differences from the list predicate we've seen in the lectures. In the parameter, for example, we see a funny plus symbol for x, but not for alpha. This distinction is to ensure automation and decidability in Gillian, but from a purely logical standpoint, this distinction does not matter. We will discuss about the differences in more details in lecture 4. We also note that we use this semicolon symbol to denote the disjunction. And finally, we note that we do not explicitly existentially quantify the variables in the non-empty list case. The variables v, y, and beta, which are not given in the parameters of the predicate, are implicitly existentially quantified. Now, let's look at the recursive list length function. As you can see, we have a separation logic triple in the form of the precondition, the function itself, and finally, the postcondition. The function itself is identical to the list length function we've seen in the lectures. The only difference is that we have this assert statement that is used for fresh variable rename. We note that this is not required and the verification can be done without this statement. This will be covered in more detail in lecture 4. The precondition is also identical to the one in the lecture notes. We only note that x here is referring to the program variable x, which is given in the parameter. And finally, we have logical variable x and logical variable alpha, which are denoted with a hashtag at the beginning. Finally, postcondition is also identical. Note that here we have len, which is an inbuilt Gillian logical function that returns the length of the list alpha. Ultimately, this triple is stating that assuming the precondition holds, if we run the program and the program terminates, then it must be the case that the postcondition holds. Now, before we start verifying this program, we immediately observe there is a blue squiggly line in the postcondition. This blue line indicates that the verification has failed, specifically during the process of checking whether the final state matches the postcondition. This is an immediate and quick feedback provided by the Gillian language server. Of course, if we want to see why the verification failed, we can use the interactive debugger to see what went wrong where. So when a separation logic triple is given in Gillian, a verify button will appear below the precondition. This will allow us to start an interactive debugging session with the execution tree visible on the right-hand side and the current state of the program given on the left-hand side. Recall that the state comprises the program stored in the heap, but it also comprises additional information such as which predicate holds at the current state and which additional constraints exist in the current state. These are very similar to the intermediate assertions that you've seen in the proof sketch. Let's try debugging this program. So like in the proof sketches for the if-else command, where we essentially branch based on the Boolean condition, we also branch in the tree based on the Boolean condition. Here, the execution tree is trying to branch based on whether x is null or not. We can choose a particular branch and execute the program step by step. And let's pick the branch where x is not null. Whereas in the proof sketches, we had to unfold the list predicate and acquire the fact that alpha is not an empty list, Gillian is smart enough to infer this information and unfold the list predicate automatically. We can see this from the current state at the left-hand side, where we see that alpha is v cons beta, where v and beta are acquired from unfolding the list predicate. We can continue running the program step by step. And we note that the error seems to be at the end. Let's expand on this. While there are a number of things going on over here, the main important part to focus on is that the verification seems to be failing at the condition where the return value is not equal to the length of alpha, which is denoted in the postcondition here. Now, we can see what the problem is by looking at the final state. Alpha is supposed to be v cons beta, but when we look at the return variable, which is n in this case, this is equal to the length of beta. So the problem is the return value does not accommodate for the extra element that was generated from unfolding the list. So the fix here would be to update this n to accommodate for that extra variable v. So let's try running this program, re-verifying this program. Instead of running the program step by step, let's try running the entire program at once. So as we can see, we have now explored all of the possible branches, and we see that for every branch, the final state matches the postcondition. This means the function has been fully verified. That is, the implementation of the list length function fully conforms with the specifications. Now let's have a look at the iterative version of list length. The function here is also identical to the one seen in the lecture notes, and the specification is also identical to that of the recursive list length function. As with all while loops, a loop invariant must be given, which is given here before the definition of the while loop. This function verification is more involved because the loop invariant includes the list segment predicate, where the list segment predicate is also defined at the top here. This list segment predicate is also identical to the one as you've seen in the lecture notes. When entering the while loop body, we know that the loop invariant must hold at the beginning and at the end of the loop body. When we dereference y here, we know that the list must be non-empty, so Gillian would automatically unfold the list predicate and expose the binary cell predicate. The idea is that at the end of the loop body, the list segment predicate will append this binary cell predicate and match the loop invariant again. However, this process is not automatic. We are required to prove that the list and list segment predicates are related. As we've seen from the lecture notes, we can apply the lemma that does exactly this, where the lemma is given at the top here. So let's apply this lemma. Finally, at the end, because we have the list and list segment predicate, we must join them to have one full list predicate to satisfy the postcondition. Similarly, we apply the appropriate lemma here at the end. So we have this list seg to list lemma. And we can see that the function fully conforms to the specification. We can check this by running the interactive debugging session and run the entire program. So as you can see, everything matches. And even within the while loop itself, we see that everything is fine. We'll go into more details about how to analyze the while loop in lecture 4. And that's it. I hope you have a better understanding on how separation logic-based verification works in practice. In the upcoming lectures, you will learn more about how these tools work in more details and the theory behind them.